This is 5.5. Let's now talk about SDN's control plane. Well, you'll see it's very different from traditional routing. For example, OSPF, BGP, these routing protocols or routing algorithms will be implemented and running on every router in the network. So it looks more like this. In each router, we do have the data plane where we have the forwarding tables. The forwarding tables are the result of computation of these routing algorithms that runs in the control plane inside each router. So you see, routing algorithm running on each of these routers. So they kind of work distributedly, but also collaboratively to come up with the forwarding table. And so we could install them down to the data plane. But in the software-defined networking paradigm, things are going very centralized in the control plane. That is also saying the routers here do not implement route computation component. So the functionality of the routers are kept very, very simple, only the forwarding part. So we don't need a flow table here to allow forwarding. And the flow tables are now computed by a central unit called a remote controller here. Okay, and that's why in SDN we say the paradigm is very centralized. Now, this remote controller could be something that's really big, containing many subcomponents. So what happens nowadays is also that part of the remote controller might be executed on one of the powerful machines and the other part on another machine. So if you think about it this way, hey, the remote controller is actually also distributedly executed. So why is this called centralized? Well, physically the remote controller is distributed, but logically it's still one unit, one big component. So that's why we say this is a logically centralized control plane. Now, the remote controller establishes these open flow channels to the control agent. So this is actually inside the data plane of the router. And this is also the channel that allows the remote controller to install these flow tables into the data planes of the routers. Let's pause here and ponder a little bit more. You see this guy here in charge of calculating all the routes for everyone in the network. You see, there's need of storing the network topology in the remote controller. The remote controller will also need to do the route computation for every possible source to every possible destination. So both the storage, both the computation, centralized. Now, we call link state routing, Inside the router, we also store the network topology. But once we have the topology, we call the Dijkstra algorithm. So this router is going to calculate the shortest path tree rooted from the router itself. And every router is going to do the shortest path tree computation themselves. So computation part in distance vector routing is distributed, while the storage part is centralized. And yet we don't like link state routing too much, We complain that this is not going to be very scalable. Therefore, we introduce distance vector routing, where each router stores only local information that makes also the storage part distributed. So the load of these distance vector routers are much lower. So DV, the total distributed solution. While the SDN's centralized control plane being a total centralized solution. From link state to distance vector, we're trying to make things more scalable. Now, SDN, a new paradigm, seemingly is drawing us backwards, pulling us back, making things even less scalable. Why? Why do we do such a thing? We actually did that for a very good reason. To make the network easier to manage. So the first reason is this. It's the same reason that we like sometimes link state routing better than distance vector. If you recall, in distance vector, if we have a route malfunctioning happening or the network admin misconfigured a particular link such that it's shorter than it is supposed to be. Yeah, it's going to take several iterations for distance vector routing to converge to the true path. So during the time, packets might be looping and looping and looping, not going to the destination. So we ended up having a network outage, so to speak. But with the centralized control plane there in SDN, the network admin, having a total view of the network, knowing the statistics of every router and every flow, he or she will be able to detect if there's a faulty route earlier. As a result, removing the faulty route, generate the correct route, and test it a little bit before installing the route into the routers. So what's nice about SDN's centralized control plane is debugging, testing, removing the routes, installing new routes. These are all made very simple so that it's harder to have a misconfiguration, and even if there's a misconfiguration, we could recover quicker. The second reason is this. In SDN, we do have a greater flexibility of traffic flows. Now, link state versus distance vector. Link state is easier to manage, just like the SDN's routing. But SDN's routing can do flexible traffic flow management while link state routing doesn't. Link state routing there, as a routing protocol in the traditional network, it's very hard to manipulate how the traffic flows the network. Let me give you a couple scenarios so you see how hard it is. Now, here's the first example. The source is on the left and the destination to the right. So expect traffic coming from U, and that is supposed to go to Z. Let's assume also this network here is running the link state routing. Now, the Dijkstra algorithm says, it's going to take the shortest pass. And so we get the blue pass below here. The pass cost is only 4, the shortest among all. But if in the next point in time, the network admin suddenly would like to enforce a certain policy or enforce a certain pass, let's say for the traffic from U to Z, let's take this pass, UVWZ, which is this red pass above. What can we do? What can the network admin do? Yeah, I know you took the course. You know how Dijkstra algorithm works. You know that, hey, if we don't change the routing algorithm, we'll have to change the link cost this way. So the pass cost for the red pass is only 3, which is less than 4. Therefore, link state routing is going to redirect traffic, starting now, through the red path. But you see, link cost there is the only control knob allowing the network admin to change or enforce a specific pass. And you can probably imagine that, for a certain network, if there are other flows going, in order to change the link cost such that all the flows stay the same and only one flow change, it could be very difficult. So link cost being the only knob, not good, not flexible, and sometimes not possible. This is the second scenario. It's based on scenario 1. So the only difference is this. The network admin this time wants to split traffic from U to Z 2 ways. Half of it goes this way and the other half of it goes this way. Because by doing so, we kind of balance the load this way as well as this way, so the potential of running into congestion is lower. Therefore, we speed up the transmission overall, for flow UZ. But the challenge here is, how would the network admin be able to configure the network such that the traffic will go both ways? If it's simply link state routing, there's no way. But in the OSPF implementation of link state, in OSPF we allow multiple same cost paths. So the network admin here will need to be very careful configuring the link cost here, 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 as well as here, 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 such that the two paths are simultaneously being the shortest path from U to Z, and equal paths from U to Z. Yeah, OSPF might be able to do it to some degree, but again, you can imagine there are other traffics that needs to go through the same network, right? Changing these link calls help the flow UZ, but what about the other flows? This is scenario 3. Again, we have traffic from U going to Z. And this time we pick this path above, UVWZ. And U is going to send traffic for some time until the network admin observe this link here, WZ, getting really busy and there's some sort of congestion building up. So network admin will say, hey, let's avoid sending more traffic over link WZ. And in the meantime, there's another flow coming, coming from router X going to router Z. The network admin, to try to avoid sending more traffic along link WZ, would really like this flow travel this other path instead, the blue path. You see here, traffic from W then can go WYZ instead of going again on WZ. But is this possible? Well, actually, no way. Not if you change the link calls. Not even if you change the routing algorithm. As long as it's still the traditional IP routing, traditional IP forwarding, which is destination based. Having a blue path in the meantime, having a red path, and in the meantime having a blue path like this is not possible. Why? When the red path is going, in router W here, there's going to be an entry saying for destination Z. The outgoing interface is going to be link WZ. And that is why this red flow here can check up the destination and then go on link WZ. But you see, traffic coming from X here, traveling the blue path, arriving also in W, will also be looking up the forwarding table here. And it's going to match destination Z. You know what? The forwarding table says go this way. Okay, traffic must go on WZ if this is the traditional forwarding, traditional routing. So you see the need of SDN as well for such a scenario. Yeah, with those scenarios, you should see that the network admin does need to, be able to control the traffic flow flexibly. Well, to speed up transmission, to reduce congestion level. But in the meantime, you also see in these scenarios, the traditional routing, traditional forwarding, does not actually provide the flexibility that the network admin would need. Yeah, so SDN being very centralized in the control plane is exactly to empower very general table-based forwarding. Okay? As the traditional routing, traditional forwarding does not allow us to manipulate the flows easily. Centralized control plane here, we could calculate the routes based on an algorithm, and then tweak specific routes manually and add those into the table before distributing the table to the routers. There you see a much higher flexibility.